So then, when you want to make a conversion from this WGS84 coordinates to these local grid coordinates, you need to go over several steps, and different type of information is actually needed to make this conversion. So first of all, if you want to make a conversion between this WGS84 coordinates, so then, as I said, if you want to go from this native Cartesian XYZ coordinates into geodetic latitude and longitude and height, then you need to know the parameters of the ellipsoid. So in case of GNSS technology, we always use the WGS84 ellipsoid. If you want to convert, or if you want to basically express coordinates in some kind of local system, then you need to perform something which is called a transformation. So transformation, there are different transformation models. The most common one, and the one which is also supported by ITCM, is called classical 3D transformation, which once again uses these free shifts, free rotations, and the scale factor that will basically allow you to convert this Cartesian XYZ coordinates to Cartesian in the local system. And I will show you later what this actually means. And the next step, when we are already in this local coordinate system, such as this Gauss-Kruger, then once again, applying the parameters of the local ellipsoid will bring you to the local latitude, longitude, and height. And as I said, from these local latitude, longitude, and heights, for practical reasons, it makes sense to basically convert the coordinates into something called grid coordinates, so typically easting, northing, and height. And then the step that you need to do here is to apply some kind of projection. So, and why we need to do that, to do this, so typically, as I said, there's all instruments such as total stations, they typically perform measurements of angles and distances, which means that they work in some kind of horizontal system, and basically with some vertical heights. And GNSS works as in this XYZ Cartesian geocentric system. So in order to make this combination of different measuring devices and methods, then you need to basically know these parameters, how to convert the coordinates and transform. Then, if we take all this into consideration, that typically the coordinate systems that we can define or we can use always consist of the transformation, the local ellipsoid, and the projection parameters. And that finally allows you to convert or to transform your measurements, which are in this WGS84 or ITRF GNSS system, into the local grid system, which basically can be used by the local surveyors or mapping agencies, etc. So when we talk about these transformations, so, or actually this is not really a transformation, this is just something that we call a conversion. So as we said, the native coordinates are x, y, z, and if you want to convert into this WGS84, latitude, longitude, and height, all you need to know are the parameters of the WGS84 ellipsoid. So once you do that, then there are basically equations that allow you to convert back and forward. As you could have seen before, Spider can do it immediately by selecting the coordinate types. The next step, or the transformation, is already a bit problematic. So here, this point P can have coordinates in two different coordinate systems. If this black one is the WGS84, so this is the one used by GNSS, and the local system looks like this. So once again, local Cartesian system. So the point can be expressed in both of these systems, and in order to basically compute this kind of transformation parameters, typically what you need to know are the free shifts of the origin. So we will bring this origin to here, to this point. Then rotations of axis, So 3 rotations of axis X, Y, Z. And in case that you are using a different basically scaling, then the scale factor is another parameter. So in total, 7 parameters are needed to compute transformation between 2 different coordinate systems, X, Y, Z. So this type of approach is called a classical 3D transformation, very often used in basically in surveying or in geodesy. So when we go back to this diagram, so in order to go from WGZ4 XYZ Cartesian to the local XYZ, you need to know the parameters of the transformation. So that's the classical 3D transformation with free shift, free rotations, and scaling is the most common one used, and it's also directly supported in Spider. So you will see that in fact you can configure this type of coordinate system and send together with real-time corrections to the rover, and the rover can immediately apply all this and get results directly in easting, northing, and height in this Gauss Kruger, for example. So we are already in the local system in XYZ. If we want to go from the local XYZ to the local latitude, longitude, and height, so this so-called local geodetic coordinates, once again, all we need to know are the parameters of the local ellipsoid. So in this case, in the case here, this would be the ellipsoid Clark 1880. That would bring us basically to latitude, longitude, and height or geodetic coordinates. And the next step is then basically this projection of latitude, longitude, and height into some kind of grid system. This last step, basically there are different types of projections that can be used. Each of them has different distortions because there is no projection without any distortions. This is something you should remember. So for the type of your country, the shape of where you are located, you can easily define a best projection that will basically incorporate the smallest, I would say, distortions due to the projection. And generally speaking, there are 3 types of projections: azimuthal, conical, and cylindrical. Cylindrical is the mostly used ones, I would say, when it comes to practical realizations. Azimuthal are not so often used because they have some significant distortions. Conical projections, they are very often used in Europe, in countries which are located in these northern areas. So these are the types of projections, and then there are different implementations. So for example, cylindrical projections, very famous is so-called Mercator. So this is one of the mostly used projections. So when you have a look at these maps, when you see that you see everywhere the tourist maps that show the whole world. So these are typically in this Mercator projection. So the Gauss Kruger, if I remember correctly, it's also the cylindrical projection, but it is rotated by 90 degrees. So this is this transverse Mercator projection, and we say it is conformal because it keeps the angles undistorted. So only the distances are distorted in this type of projection. So as I said, there are different types of projections which you can use, which you can apply basically to convert the latitude, longitude, and height into some kind of planar system. And once you do that, then the coordinates are not expressed anymore in latitude and longitude, but most of the time they are expressed in so-called easting and northing, or lowercase x and lowercase y coordinates. So once again, if we go from this local geodetic coordinates, latitude and longitude and height, to local grid, typically easting, northing, and height, then what you need to know are the parameters of the projection. And so this is the last step when we talk about moving between all coordinates types or coordinate systems, which means that when we go from GNSS measurement into some kind of local system. So once again, to make a conversion between geodetic and Cartesian, on this GNSS side, all you need to know are the parameters of the WGS84 ellipsoid. When we told this classical 3D transformation, this is used to basically transform coordinates from this XYZ Cartesian on WGS84 to some kind of local XYZ coordinates. And then once again, going to geodetic latitude, longitude, you need to know the parameters of the local ellipsoid. In case here, this is this Clark 1880. And to go from latitude, longitude, local geodetic to this grid coordinates, easting and northing, or lowercase x and lowercase y, you need to know the parameters of the projection. So Gauss-Kruger, here it is this transverse Mercator cylindrical projection. So this is the way how, this is basically the whole process of how different types of coordinates are used, can be transformed or can be converted when it comes to GNSS technology. Right. So now, how can we do that in Spider, or what can we do in Spider in terms of this? So in Spider, I would say in SpiderNet, which one is that? We have a section here on SpiderNet called Transformations, where we can configure all these partial steps to go from GNSS measurements in ITRF 2014, EPOC 2018.49 to a local grid system. Now, how can you do that? Once again, I have some presentation that will show you this. Do you find it? It's on SpiderNet. Yes. Transformations. So this is a module which allows you to configure any type of coordinate system, basically. Yes. Normally, you will be able to see the parameters of transformation in the rover. So you will see, because we are going to configure coordinate system together with transformation with everything that can be actually sent together with real-time corrections. So together with RTK corrections, the rover will also receive these parameters. And then if the user can dig inside the data, the information, then in fact it can find the parameters of transformation. It's not obviously shown directly, but yes, it is a way that that the end user can actually see that. So the section coordinate systems in SpiderNet. So they said that the GNSS measurements are performing this WGS84 or ITRF coordinates, but this is extremely impractical. So this is why it is necessary to define this transformation and coordinate system for practical use mainly. And so the advantage to do it in Spider is that the end user doesn't need to care about some control points, some measurements on the control points and computing local transformation models. If you can define one global transformation for the whole country, and this can be distributed directly from SpiderNet, which means that there is no interaction from the end user. The system will be applied automatically. This is the big advantage that basically end use doesn't have to do anything. So as we said, the source system is this XYZ coordinates Cartesian in some reference frame, so night year 2014. And the target system consists of, once again, the Cartesian coordinates, then geodetic coordinates based on the local ellipsoid, and then geodetic coordinates latitude and longitude, or sometimes called E and N, depending on what terminology you use. And then the height can be either defined over the ellipsoid or over the geoid. So geoid and ellipsoid is at different heights depending on what type of system you want to use. Then you can get heights either in this orthometric form, which is the one measured to geoid, or ellipsoidal heights, which are measured to local ellipsoid. And the key factor is this datum transformation. So typically we use this 7-parameter or sometimes 10-parameter transformation. These are two different transformation models which are supported by RTCM, and that can be distributed together with RTK corrections. So here we see the requirements. So here we need to know the ellipsoid, the geoid, or the projection information. So what kind of things you can see? What is available in this coordinate systems module? Typically, you will find all necessary parameters that you need to configure for the coordinate system. So typically the datum transformations, the ellipsoids, so residuals or these geoid models, and then projections. So all this is available, so you can basically configure system that fits to your local basically coordinate system. So first thing to define is this transformation. So something you have seen, something similar. This is the principle of transformation, that if you want to go from this XYZ to this blue XYZ Cartesians, you need to shift the origin. So typically these three shifts in this XYZ components. Then you need to rotate each of the axes, and then scaling, if necessary, can be also applied. And generally speaking, there are two models that you can use here. So if you go to datum transformation and you right-click select new, then you have two transformation models. One is called so-called Bursa-Wolf, and the other one is called Molodensky-Badeka. So this is a 7-parameter transformation. This is a 10-parameter transformation. So normally, this Bursa-Wolf is used per default, unless the area that you want to transform is very small. So in your country, it's quite large. You can easily use this 7-parameter Bursa-Wolf model, and this is more or less the equation which is used. So we have this system T. This is this black one, and then we have this system S, which is this blue one. So if you want to go, if you want to make some kind of conversion or transformation between these two systems, you typically need to know the 7-parameter model, or the 7 parameters. So as we said, the translation model or vector, it is this green one, consists of these 3 shifts in X, Y, Z, coordinates of the origin. Then you have rotations. So once again, these are these grayish elements. So rotation around X, Y, and Z. And the scale factor, normally, if you go from a system which is GNSS based to another system which was GNSS based, then the scale factor will be 0. So there will be no scaling. So 1 meter in the original system will be also 1 meter in the target system. So in order to compute this transformation, then you need to have some kind of source coordinates and then the target coordinates. Molodensky-Badeka is a special model when, as I said, it's used for smaller areas, and you, in addition, are basically including some kind of pivot point for the transformation. So this is just a modified version of the Bursa-Wolf model, so it's not so interesting, but it is an option here so that you know what it means, that you have this pivot point or the origin of the pivot of the area, then it is used together with the transformation. In order to compute a transformation for systems which especially for which has been built historically like here, then what you need to have, you need to get a set of points which have coordinates in both systems. So imagine this point P, first of all, has coordinates XYZ in this ITRF coordinates, but it also has coordinates in this historical system. And basically, this is how we are going to, or we'll try to compute the transformation for Zimbabwe, that we have certain number of control points with original Gauss-Kruger coordinates. We are going to reobserve them and basically compute 7-parameter transformation based on these measurements. Right. So this is the transformation. The second step is to apply ellipsoids. So ellipsoids, they have been already introduced. So basically, you don't need to define any new ellipsoid unless you are really using some kind of ellipsoid which is non-standardized. But all the standardized, all these historically used ellipsoids are already included in Spider. So all you need to do is to select your Clark 1880, for example, and basically use it for conversion of coordinates in the local system. This means that they're already in use. So Spider already comes with some pre-configured transformations and coordinate systems. So if some of these ellipsoids are in use, like WGS84, for example, then it has this exclamation mark icon here. So GRS is another ellipsoid which is used with GNSS. It just has the same parameters as WGS84, or maybe it's not exactly the same. There is some difference here at the end of the flattening. So, but those that have this exclamation mark are already in use. But you can also define your own ellipsoid if this is necessary here. Right. So then, if you define your coordinate system, then the target ellipsoid is shown then here. The last section that you need to, not the last section, but another section that you need to configure is a projection. As you can see, we support different types of projection also in Spider. So this azimuthal projection, conical, cylindrical, and so normally, well, it's correct that since we need to transmit the coordinate system, then we need to use only parameters or transformations or projections which are supported by this RT0 standard. So not all projections are available, but Gauss-Kruger, which is good news, is part of this. You see, actually there are already some pre-configured Gauss-Kruger projections here. This is the transverse Mercator projection type. This is supported, so we can use it together with your real-time corrections. So if you would like to configure your specific projection, then you can always do it in this section, projections. So plenty of them supported. And then once you select your projection type, then you need to configure the parameters. So typical parameters for projections are some kind of false easting, full northing, the latitude of natural origin, the longitude, or the meridian, the reference meridian, etc., etc. So this is quite a large topic, and as I said, this is more or less somebody who has some background in mapping. Then you can configure whatever you need here. The last thing that you can configure are these residual models. So in residual models, we understand this, for example, the geoid model is kind of a vertical residual model or a horizontal residual model. So this would basically be used if you would not have some inconsistent coordinate systems that basically doesn't give good, I would say, coincidence, or not coincidence, good convergence. So then you need to apply some additional residual models to bring transformation to the state that it doesn't give too high residual errors. This is what can be done. And once you do that, you can configure your target coordinate system uh, consisting of the datum transformation, ellipsoid, residuals, and projections. So now, what we are going to do, we are going to configure some sort of dummy coordinate system that will look like your Gauss-Kruger. The only thing that will be missing will be the transformation. So, do you know the parameters of your Gauss-Kruger? Probably not. Yeah, we can do just some example. So here we are, target coordinate systems. As I said, this is something we don't know. This is the transformation between the ITRF 2014 to the local XYZ. There are two models, as I said, Bursa-Wolf and Wolensky, so most probably are going to use the 7-parameter transformation, free shifts, free rotation, and scale factor. And the target ellipsoid in this case will be Clark 1880. This one. And so we don't know anything about the horizontal vertical quality of this. So we are going to call it DSG, because it will be transformations from your ITRF to basically some kind of local Cartesian system. So this would be the first step here to define the transformation. For ellipsoid, we already have the Clark 8080. You see, since we used it already, then it is with this exclamation mark. At the moment, we have no residual models, but for projections, unless it is the standardized one, then we can define our own Gauss-Kruger. It's basically this transverse Mercator. So I will call it Gauss-Kruger Zim for Zimbabwe. And here typically you need to configure the so-called false easting, false northing, latitude of natural origin and latitude of natural, longitude of natural origin. So basically, where is the beginning of the projection? So, latitude of origin, yes. Yes, we can change to south, no problem. If you could find this information, then we can directly configure it. False easting usually is something like 500,000 meters. 1 million. Mm-hmm. Is it? This is not UTM. It's Act 1950. The Act 1950 is the atom. Mm-hmm. This one is vacuum modified. Mm-hmm. So let me check. What is our latitude? They're trying to find out. Yeah. Because you can define it in many ways, you know, since this is not a universal TM, it's not a UTM. So for UTM, it's easy. You have this 3 degrees, 9 degrees, I don't know, 15 degrees, this 6 degrees. Basically, every 6 degrees you have the zone, and latitude of origin is 0 because it is measured from equator. But since you have your own Gauss-Kruger, then it can be defined, you know, in any way. It can be defined from the center of the country, for example, which would not be something which is recommended because you would have negative values, negative signs for the coordinates. But Okay, arc 9050 Zimbabwe projection. I found something on the internet. Arc 50. I found this. Is this correct? Oh, it's on the internet. So arc 50 UTM zone 35S, in fact. So the projection parameters for this transverse Mercator is so this. So origin latitude, longitude is 27, latitude is 0, and the scale factor is 9996. Clark 8080 arc. So it is different than the one that we have. So it is slightly different. 249145. 249. 249145. This is the same, but the flattening might be different. 293465. Yes. So actually, this ellipsoid seems to be slightly different than the one that we have. So in fact, it is also necessary to define a new ellipsoid for your projection. So first of all, let's define this transverse Mercator. So 1, 2, 3, 4, 5, 6, 7 zeros, 10 millions falls northing. So if you go back, transverse Mercator. So full northing is 10 millions. 1, 2, 3, 4, 5, 6. Then false easting is 500,000. 500,000. Latitude of origin is 0. Yes, 10 millions. Latitude of origin is, sorry, latitude of origin is 0 and longitude is 27. Latitude of origin 0, longitude of origin 27. And the scale factor is 0.9996, if I'm not mistaken. 9996. Okay, so these are the parameters for your projection.
Yeah, on nothing.
No, south. Map datum parameter R50. What is this? Clark. Same major axis. I see some. Actually, you also have some transformation for this arc 50. Smolodensky. Do you know about it? This free parameter transformation. Do you know what it is?
Which one?
This one. So this arc 1950. Do you know what it is about? No. Okay. So anyhow, this is how this Gauss-Kruger so I will call it Gauss-Kruger Zim. And now, all right. So now it is here. So we have projection. Now we need to go to ellipsoid and define this Bessel ellipsoid, or not Bessel, this Clark modified. So press here, right click and select new. And the name, which I found on the internet, is called Clark 1880 arc. All right, so Clark. Arc, and the parameter, the semi-major axis is the same. So 6378 249.145. The difference is the flattening, so it's 293.466, if I remember correctly. Clark 1880 arc 4378 249.145 and 295.466 3077. Right. So this is this Clark arc. It's very close, but the flattening is different. So it's the flattening is bigger, slightly bigger, so it is flatter than the standard Clark. So that's why they call it this Clark arc. And somebody created DSG05. All right, I will just select properties here. I will select a different. You created it, yes. Okay. There is Clark arc. Clark arc 1, okay. It looks like I'm seeing W. Everything I see twice. So And so I don't know where. So did you manage to find something? Because here they say, because I found some group discussion about projection in Zimbabwe. So this is where you see all these parameters. So that somehow somebody was asking. Uh, so this is for map info. Are you familiar with map info? Are you using map info software now? Yes. Um, Anyhow, so here they have published these parameters, and I'm surprised to see this. So these are basically the shifts of the origin of the Cartesian coordinate system. So maybe we could find something else. Yeah, well, so what we can still use these free shifts, and I will call it ARC 1950, and you can test it with whether it will work with the rover or not. So I'm going to apply also these free translations of the origin of the coordinate system. So once again we go here, and they're talking about these free shifts. So the first shift to define is this -1 for free. So it's for x -1 for free. -90 and -294. -90 and -254. And according to this thread, this system is called ARC 1950. So not DSG, I will call it ARC 1950. All right. So here, so this is the datum transformation, and coordinate system. If I right-click select a new one, then we need to select everything here. So datum transformation will be this ARC 1950. Residuals, we have no residuals, and projection will be in this case this Gauss-Kruger Zim. Here you can define on which plate we are. So this is this African tectonic plate, and the height system. As I said, you can have two height systems. One is related to the ellipsoid. These are ellipsoidal heights. So this is so-called geometrical heights. Or you can have heights defined to the geoid model. So this is this approximation of the Earth. So these are called physical heights. And you can even define the area of validity for this coordinate system. And now I'm going to call it ARC 1950 Zim. And if I press OK here, then it will appear on the list of available coordinate systems that can be typically sent out together with RTK corrections. So you can try to create something similar. Just for practicing, and I'm wondering if I can find something else on this. Yes, did you manage? And you cannot. for you. Successful. Okay, I will. Ah, it's user. Okay, I see who you are. All right. Oh my God. How about you? Can you please log out and log in again? Just close the connection and start again because I need to find out who you are. Yeah, but this is yeah. I know your name, but I don't know what is your Windows login credential. So it can be something else. If you just close the connection and reopen, then I should see it here.
Just what is fine.
Spider net, yes.
If you open the client, find the client. No way. And now network. Okay. Moment. Okay. Moment. No.
But you still you will not be able to create anything because you are a viewer. So this is your own. All right. Okay, now if you log in, you should be administrator. You should be able to.
Yeah, first no. We are administrating now. You should have access to the
So usually most they use WGS to come up with area.
Okay.
You can use WGS.
Yeah. So yeah, I found it also another page. Exactly, this one is this ARC 1950. That's what I call it, including this free shift. Uh, so basically, this is this should be it. Obviously, we'll have different results. So when you measure your control points, then uh, but you are using still this projection and also this Clark 1880 arc. Yeah. For the local system. Gauss conform. Okay, so the only difference then will be these parameters of the projection. Mm-hmm. So that's your plan to different zones, different. Mm-hmm. Okay. Mm-hmm.
So this is how we are going to use it in terms of our zone.
But you mean this is for the new system or the current one, the Gauss Krug, or this is for the new datum that you want to define? Or this is this.
For the new data, when you calculate parameters,
Mm-hmm.
you need to know that
Yes.
so by the moment you observe
Mm-hmm.
the ordinate GPS, you want to apply the GPS.
Yes, sure.
When you calculate
Yeah. Okay, but I was wondering. Okay, that's fine. So once you have configured this ARC 1950, I call it Zim. So you can close this transformations manager. Actually, we can go to real-time product and we can create a new near site G4. I will call it near G4 arc. What is it called? 115. I forgot already. Arc 1950. Okay. Arc 1950. And so here, coordinate reference frame. So we are going to use this product marker coordinates as the reference frame. So this will be the starting point, our ITRF 2014 coordinates. And then the target coordinate system will be ARC 1950 ZIM. That's all that you need to do. And then, oh yes, sure, we need to make a different mount point. We'll call it ARC 1950. So I created a new product, which is called near G4 ARC 50. And as you can see, the target coordinate system, which it will use, is this ARC 1950 ZIM. So it includes the transformation, the projection, Gauss-Kruger according to parameters which we saw before. This new ellipsoid, this ARC 1980, Clark 1980, Clark 1950 ARC plus plus the projection. So all this is sent to the rover, and the rover needs to have a special setting called automatically receive coordinate system. So this is just one switch in the rover configuration, and the rover will automatically detect or read these parameters from the RTK correction stream and compute its position first of all in real time, and then transform the coordinates directly to this local coordinate, so xy or easting, northing, and an ellipsoidal height. So then the rover operator will directly see this grid coordinates on the rover. These grid coordinates can be stored in the log file, in the file on the rover, and just exported directly as a text file. Already, everything transformed into the local system. So this is the idea. Once you have done your transformation computation, to implement it also here and then send to the end users, so you can directly basically do that. And the same we can do also for post-processing services. So in but here the process is slightly different. So if you still need, I can. Okay, so you have already created some, yes, some of your coordinates